Something is pulling you into your chair right now. It reaches across the room, across the planet, across the entire solar system, and it has never once stopped. Gravity is the most familiar force in the universe, and yet is the only one we cannot explain at the quantum level. Every other force has a particle, a messenger, something that carries the push or the pull from one place to another. But gravity? We have never found one. Not a single graviton has ever been detected. Not one. And here is what should genuinely unsettle you. The reason we haven't found it isn't that we're looking in the wrong place. It may be that finding it is physically impossible with any technology that could ever exist. Ever. If this kind of deep dive into the real frontiers of physics is something you enjoy, a like or a subscribe would honestly mean a lot. It helps this channel grow more than you might think, and it costs you nothing. Now, let's begin. Every force that has ever acted on you has a carrier, a particle, a physical messenger that travels between objects and makes the push or the pull happen. This is not a metaphor or a convenient shorthand. It is the actual mechanism by which nature operates at its most fundamental level. And for 3 of the 4 forces that govern everything in the universe, we have found those messengers, confirmed them in experiments, and built precise mathematical theories around them. It is curving the path of the moon around the Earth, bending the trajectory of light itself as it passes near a massive object, and holding every single star in the Milky Way in its long, slow, gravitational embrace. Gravity is so woven into the fabric of your existence that you barely notice it. It is just there, constant, reliable, invisible, and we have absolutely no idea how it works at the deepest level. That statement might sound strange. We have equations for gravity, extraordinarily precise ones. We can use them to land a spacecraft on a moving asteroid, hundreds of millions of kilometers away. We can predict the position of Jupiter to within meters-years in advance. We can calculate how much a clock on the International Space Station runs faster than a clock on the ground, and we can verify that prediction with atomic precision. By every practical measure, we understand gravity enormously well. But there is a difference between describing something and understanding it. And the deeper you go into the physics, the more obvious it becomes that gravity is not like anything else. It sits outside the framework that explains everything else in the universe. It refuses to fit. And that refusal has been one of the central frustrations of theoretical physics for nearly a century. To understand why, you first need to understand how physicists think about forces in general. Because the modern picture of what a force actually is, what it means at the most fundamental level for one object to push or pull on another, is deeply counterintuitive, and it is the key to everything that follows. In everyday life, forces feel direct. You push a door and the door moves. The sun pulls on the earth and the earth curves around it. It seems like objects simply reach across space and exert influence on one another. This is roughly the picture Isaac Newton gave us, and for most purposes it works beautifully. Newton's law of universal gravitation, published in 1687, described gravity as an instantaneous force acting across any distance. 2 objects with mass attract each other with a strength that depends on their masses and the distance between them. Clean, mathematical, predictive, revolutionary. But it left an uncomfortable question unanswered. How does the force actually travel? If you doubled the mass of the sun right now, how would Earth know? In Newton's picture, it would know instantaneously. The gravitational influence would update across the entire solar system at once, regardless of distance, and that bothered physicists, even Newton himself, who famously wrote that he would not feign a hypothesis about the mechanism. The question of mechanism, of how forces actually propagate from one place to another, became answerable only in the 20th century, and the answer transformed physics completely. The answer is particles. This is the central insight of quantum field theory, which is the framework that underlies the standard model of particle physics. Our most complete and most tested description of how the universe works at the subatomic level. According to quantum field theory, forces are not mysterious, invisible threads pulling objects toward each other. Forces are carried. They are mediated by particles, specific, real, physical particles that travel between objects and transfer momentum and energy between them. The interaction is not a reach across space, it is an exchange, like a game of catch played at unimaginable speed and scale. These force-carrying particles are called bosons, and they are fundamentally different from the particles that make up matter. Matter particles, electrons, quarks, and the things built from quarks are fermions. They obey what is called the Pauli exclusion principle, which means no two identical fermions can occupy the same quantum state simultaneously. That is why matter takes up space. That is why you cannot push your hand through a table. Fermions resist being in the same place. Bosons have no such restriction. Multiple bosons can pile into the same state. They can overlap. They can be absorbed and re-emitted, and crucially, they can carry force. The photon is the most familiar example. It is the boson of the electromagnetic force. When two electrons repel each other, what is actually happening at the quantum level is an exchange of virtual photons. Photons that carry momentum between the two electrons and push them apart. The word virtual here does not mean imaginary. It means these photons exist within the constraints of the Heisenberg uncertainty principle, which permits brief violations of energy conservation provided they happen quickly enough. Virtual particles are a real feature of quantum field theory, confirmed by their measurable effects on atomic spectra and on the way particles scatter off one another. The electromagnetic force has one boson, the photon. It is massless, which is why electromagnetism has an infinite range. It can reach across the entire universe. The photon has a quantum spin of 1, which is why electromagnetic fields have the mathematical symmetry properties they do. Everything about the photon and its relationship to the electromagnetic field is coherent and experimentally verified to extraordinary precision. Quantum electrodynamics, the theory that describes this relationship, is the most precisely tested theory in all of science. Some of its predictions match experiment to 10 or more decimal places. The strong nuclear force, the force that holds quarks together inside protons and neutrons, and holds protons and neutrons together inside atomic nuclei, is carried by gluons. There are 8 types of gluon, all massless, all with spin 1. But gluons behave very differently from photons. While photons do not carry electric charge themselves, gluons carry what physicists call color charge, which is the strong force equivalent of electric charge. This means gluons interact with each other, not just with quarks. The result is that the strong force does not weaken with distance in the normal way. Instead, it increases. Try to pull 2 quarks apart and the energy stored in the gluon field between them grows until it becomes sufficient to create entirely new quark-antiquark pairs from pure energy. Quarks cannot be isolated. They are permanently confined inside composite particles. This phenomenon is called confinement, and it is one of the most remarkable and counterintuitive properties of any force in nature. The weak nuclear force, responsible for certain types of radioactive decay, including the beta decay that allows the sun to fuse hydrogen in its core, is carried by 3 bosons: the W+, the W-, and the Z0. Unlike photons and gluons, these bosons are extraordinarily massive. The W bosons each have a mass of roughly 85 times that of a proton. The Z boson is even heavier, with a mass nearly 97 times the proton mass. This mass is why the weak force has such an incredibly short range. It cannot reach across atoms. It operates only at distances smaller than the nucleus itself, at scales of roughly 10 to the negative 18 meters. The mass of the W and Z bosons is not arbitrary. It comes from the Higgs mechanism, the process by which the Higgs field gives mass to certain particles through their interactions with it. The Higgs boson itself, the quantum of that field, was confirmed at the Large Hadron Collider in 2012. So the picture is this: 3 of the 4 fundamental forces, electromagnetism, the strong force and the weak force, are all described by quantum field theories. Each has its own boson. Each boson has been detected experimentally. Each force fits within the framework called the Standard Model, a mathematical structure built on the principles of quantum mechanics and special relativity that has been tested against thousands of experiments over decades without a single confirmed failure. And then there is gravity. Gravity has no confirmed boson. Gravity has no quantum field theory. Gravity cannot be placed inside the Standard Model. Every attempt to apply the mathematical tools that work brilliantly for the other 3 forces to gravity runs into catastrophic problems. The equations produce infinities, not the manageable infinities that appear in quantum electrodynamics and can be tamed through a procedure called renormalization, but true intractable infinities that signal a complete breakdown of the theoretical framework. Predictions stop being predictions and become meaningless symbols. This is not a minor technical gap waiting to be filled by a clever calculation. This is the single most profound unsolved problem in theoretical physics. And before we reach the mathematical catastrophe, there is something even more basic that demands explanation first. Something that should be the first alarm bell. Something physicists call the hierarchy problem. Gravity is almost unimaginably weak. Not slightly weak. Not weaker than expected by some modest amount. Gravity is weaker than the other fundamental forces by factors that are almost impossible to convey with ordinary language. Let us actually confront this number directly. The electromagnetic repulsion between 2 protons, the force caused by their identical positive electric charges pushing them apart, is approximately 10 to the power of 36 times stronger than the gravitational attraction between those same 2 protons. Write that out in full and you get a 1 followed by 36 zeros. 1,000 trillion times stronger. The strong force at the scale it operates is even more powerful than electromagnetism. And even the weak force, despite its name, is vastly stronger than gravity when compared at the same energy scale. Gravity is not simply the weakest of the 4 forces. It is weaker than the next weakest force by a factor that dwarfs the number of stars in the entire observable universe. Think about what this means in practical terms. A small magnet stuck to your refrigerator is counteracting the gravitational pull of the entire mass of the Earth. The entire planet, with all its iron and rock and water and molten core, pulling downward on that magnet and a tiny piece of magnetized metal the size of your thumbnail wins, the whole Earth loses. That is how weak gravity is compared to electromagnetism. Consider the nucleus of an atom. It contains protons packed closely together. Those protons are all positively charged, and identical charges repel each other with enormous force. The electromagnetic repulsion trying to blow the nucleus apart is staggering, and yet the strong force holds the nucleus together against that pressure. Where is gravity in this picture? Completely irrelevant. The gravitational attraction between protons inside a nucleus is so negligible compared to the other forces at play that it contributes essentially nothing to the calculation. Physicists simply ignore it entirely, not as a rough approximation, but because the gravitational contribution falls below every meaningful threshold of physical significance at that scale. This disparity has a name. It is called the hierarchy problem, and it is one of the deepest puzzles in all of physics. Not merely because gravity is weak, but because it is bizarre that it is this weak. The other three forces are all within a few orders of magnitude of each other when compared at the same energy scale. Gravity is not within a few orders of magnitude. It is 36 orders of magnitude weaker than electromagnetism. That is not a small discrepancy that might be smoothed over. That is a chasm so enormous it suggests some mechanism or structure we have not yet identified is responsible for suppressing gravity to this extraordinary degree. Several proposals have been put forward for why gravity might be so incomprehensibly feeble. One of the most intriguing involves extraspatial dimensions. If gravity is the only force that can propagate through dimensions beyond the three spatial dimensions we experience, then the gravity we observe would be only a tiny fraction of gravity's true strength, the rest of it leaking away into dimensions inaccessible to us, invisible to all our instruments. From this perspective, gravity is not intrinsically weak. It only appears weak because most of its influence is escaping sideways into a geometry we cannot access. This idea was proposed seriously in the late 1990s by Nima Arkani Hamed, Savas Dimopoulos, and Gia Dvali, and remains a viable theoretical possibility, though not one with direct experimental confirmation. Another approach involves supersymmetry, a theoretical framework that postulates a deep symmetry between bosons and fermions, such that every known particle has an undiscovered partner of the opposite type. Supersymmetry would, if it exists and breaks at the right energy scale, provide a mechanism for stabilizing certain mass values and potentially shed light on the vast gap between gravity and the other forces. But despite extensive searches at the Large Hadron Collider spanning more than a decade, no supersymmetric partners have been found. The theory is not ruled out, but it has not appeared where many physicists expected it to. The honest answer is that we do not know why gravity is so weak. We observe the weakness with great precision. We can feel its consequences. The fact that chemistry can operate, that molecules can form and persist, that life can exist. Partly because gravity is too feeble to crush atomic scale matter into itself. But the reason for this weakness remains unanswered. And it matters enormously when we think about the graviton. Because if gravity is extraordinarily weak, then the coupling constant describing how a graviton interacts with matter is also extraordinarily small. A force carrier that barely interacts with anything is a force carrier that is almost impossible to detect, no matter how sophisticated your experiment. But there is a more fundamental tension here than just the weakness of gravity. There is a conceptual tension between how general relativity describes gravity and how any quantum theory of it would have to describe it. And this tension is not only mathematical, it cuts to the very nature of space and time themselves. In Newton's picture, gravity was a force acting through a fixed, unchanging backdrop of absolute space and absolute time. The universe was a stage, and events happened on it. The stage itself was rigid and permanent. Forces pulled objects around on that stage, but the stage never changed. Einstein replaced this with something radically different. In General Relativity, published in 1915, space and time are not a fixed background. They are dynamic. They curve and warp in response to the presence of mass and energy. Gravity is not a force in the Newtonian sense. It is the curvature of space-time. Objects do not fall toward the Earth because some invisible rope is pulling them downward. They fall because the space-time in the vicinity of the Earth is curved, and they are following the straightest possible path, called a geodesic, through that curved geometry. What we experience as gravitational pull is the geometry of the universe itself pressing against us. This is a profoundly geometric picture of reality. Einstein's field equations relate the distribution of mass and energy in a region of space-time to the curvature of that space-time. Mass tells space-time how to curve. Curved space-time tells mass how to move. The interaction is mutual and continuous, and woven into the structure of existence itself. And the predictions this picture produces are extraordinary. The precise precession of Mercury's orbit, a small but exact deviation from what Newton's theory predicted, is explained perfectly. The bending of light around massive objects, confirmed during the solar eclipse of 1919, comes directly from the equations. The gravitational redshift of light climbing out of a gravity well, light losing energy as it works against gravity, shifting to longer wavelengths, is measured with atomic clocks and confirmed. Gravitational time dilation, the reality that time runs slower in stronger gravitational fields, is real, measurable, and built into the software of the GPS system that billions of people use every day. Without correcting for it, GPS coordinates would accumulate errors of roughly 11 kilometers per day. General relativity has passed every test it has ever been given. It is not an approximation or a placeholder waiting to be replaced, but it is a classical theory. It contains no quantum mechanics. It treats space-time as a smooth, continuous, deterministic entity. Given the distribution of mass and energy everywhere at one moment, the evolution of space-time is perfectly determined. There is no randomness built into the equations. There is no quantum uncertainty. There are no superpositions of different space-time geometries. Quantum mechanics is the precise opposite. It is fundamentally probabilistic at its core. Particles do not have definite positions and momenta simultaneously. The Heisenberg uncertainty principle forbids it. They exist in superpositions of many states at once until a measurement forces one outcome. The entire mathematical apparatus of quantum field theory is built on probability amplitudes and expectation values. The language of the framework is the language of statistics at the most fundamental level of physical reality. These are not merely different mathematical formalisms that happen to describe the same world in different notations. They represent genuinely different claims about the nature of reality. And when you attempt to apply quantum mechanics to the gravitational field, when you try to quantize gravity the way you quantize electromagnetism to get photons, or quantize the strong field to get gluons. The smooth, curved space-time of general relativity resists with a violence that is, mathematically speaking, total. In quantum electrodynamics, the electromagnetic field is quantized. Small fluctuations in the field correspond to photons. The field is not continuous, it is made of discrete quanta. This quantization procedure is well understood and produces a theory of extraordinary accuracy. If you attempt to do the same thing for the gravitational field, if you try to say that small fluctuations in space-time curvature correspond to gravitons, to discrete quanta of the gravitational field, you run into a problem that is not merely technical. Quantizing space-time is not the same as quantizing a field sitting on top of space-time. Space-time is not sitting on anything. It is the structure within which everything else exists. To quantize it means making the structure itself uncertain and probabilistic. It means asking what it looks like for the geometry of space and time to exist simultaneously in a superposition of different curved configurations. That is not a question we know how to answer in any consistent way. The mathematical machinery breaks down. And it breaks down for deep reasons connected to the fact that gravity is not a force propagating through space-time, but is literally a property of space-time. You cannot separate the gravitational field from the arena in which physics happens, because they are the same thing. This is the dividing line. On one side, general relativity, a flawless classical description of gravity as curved space-time. Perfect at large scales, completely deterministic, describing the cosmos with extraordinary success. On the other side, quantum field theory, a perfect quantum description of the other three forces, built on probability and particle exchange, producing mathematical catastrophe whenever gravity is introduced into its equations. Both frameworks are correct within their domains, both are used every day in physics and technology, and they cannot both be the final word, because a universe described by two mutually incompatible fundamental frameworks is a universe we do not fully understand. The most physically concrete location where this incompatibility becomes not merely theoretical but mandatory is the interior of a black hole. General relativity predicts that when a sufficiently massive star collapses at the end of its life, the inward gravitational pressure overwhelms every other force in nature. Electron degeneracy pressure fails. Neutron degeneracy pressure fails. Nothing stops the collapse. The mathematics of general relativity follows the infalling matter all the way to a point of infinite density, a singularity where the curvature of space-time becomes literally infinite and the equations of the theory produce meaningless outputs. The theory predicts its own destruction. It reaches a point and says, "Here, I stop working." Quantum mechanics says something different. Infinite densities are unphysical. The Heisenberg uncertainty principle imposes a fundamental limit on how precisely position can be defined, which translates into a fundamental limit on how tightly matter can be compressed. Something must happen at the Planck scale. Some quantum gravitational process must intervene that prevents a true singularity from forming. The smooth, deterministic geometry of general relativity must give way to something else. But quantum field theory, in its current form, has no language for describing what that something else is, because it requires a fixed background spacetime, and inside a collapsing black hole, the background spacetime is the very thing that is failing. Both frameworks must apply simultaneously at a black hole singularity. Both break down simultaneously at that same point. This is not a distant theoretical concern confined to the blackboards of research institutes. Black holes are observed throughout the universe. The center of our own galaxy harbors one with a mass 4 million times that of the Sun. Every one of those objects contains, according to our best theories, a place where physics as we know it ends. The graviton is the particle that would belong to the theory capable of describing what actually happens there. And we do not have that theory. The graviton sits exactly at this fracture line. If gravity can be quantized, if a quantum description exists, that resolves this tension without destroying either framework, then a graviton must exist. A particle that carries the gravitational interaction the way photons carry the electromagnetic force. A quantum of the gravitational field. Its properties would be dictated by what the mathematics demands. Its behavior would be unlike anything we have ever detected. And the story of why it has never been found, and why finding it may be physically impossible, begins with understanding what this particle would actually have to be. If you want to know what a graviton would be, the place to start is not speculation. It is constraint. Physics is extraordinarily good at telling you what something must be before you have ever seen it. The logic is tight and unforgiving. If gravity is a quantum field, then the graviton is not a particle we get to design freely. Its properties are determined in advance by the mathematics of the theory it would belong to. The structure of general relativity, the requirements of quantum mechanics, and the known behavior of gravity at large scales all combine to draw a precise portrait of a particle we have never detected. And that portrait is, in several ways, deeply strange. Begin with mass. The graviton, if it exists, must be massless. This is not an assumption or a simplification, it is a requirement that follows directly from the behavior of gravity at large distances. We know from observation that gravity is a long-range force. It reaches across the solar system, across galaxies, across galaxy clusters. There is no distance at which gravity simply switches off. It weakens with distance, following an inverse square law with extraordinary precision, but it never vanishes entirely. It extends, in principle, to infinity. This long-range behavior is a fingerprint. In quantum field theory, the range of a force is intimately connected to the mass of its carrier boson. Specifically, the range of a force is inversely proportional to the mass of its mediating particle. If the carrier boson has zero mass, the force has infinite range. If the carrier boson has any mass at all, however small, the force has a finite range. It falls off exponentially beyond a characteristic distance determined by that mass. This relationship comes directly from the mathematics of relativistic wave equations, and it is not an approximation. It is exact within the framework. The weak force is short range. It operates only within the nucleus, at distances smaller than a proton. And its carrier bosons, the W and Z, are massive, each weighing in at tens of times the proton mass. Their mass is precisely why the weak force cannot reach farther. The exponential suppression kicks in almost immediately, and the force is essentially zero beyond nuclear scales. The electromagnetic force is long range, extending across the cosmos. The photon is massless, exactly zero, not approximately zero, not negligibly small, exactly zero mass. That is why light travels forever through empty space without slowing down or fading into nothing. The masslessness of the photon is not a coincidence or a lucky accident. It is enforced by the symmetry structure of electromagnetism, a deep mathematical symmetry called gauge invariance that forbids the photon from acquiring mass. The symmetry and the masslessness are inseparable. For the graviton, the same logic applies, but in an even more constrained form. We observe that gravity follows an inverse square law at astronomical distances. Any mass on the graviton, however tiny, would cause gravity to deviate from this law at large enough scales. We have tested the inverse square behavior of gravity across enormous ranges, from laboratory scales of fractions of a millimeter up to the distances of the outer solar system, and it holds. Observations of gravitational effects across galaxy clusters and across the universe provide upper bounds on any possible graviton mass that are extraordinarily tight. The most precise cosmological observations constrain the graviton mass to less than roughly 10 to the negative 32 electron volts. An electron volt is already an incredibly tiny unit of energy. The graviton mass must be smaller than that already minuscule unit by 32 orders of magnitude. For all physically meaningful purposes, the graviton is massless. A massless graviton travels at the speed of light. This follows immediately from special relativity. Any massless particle must travel at exactly the speed of light, not approximately that speed, but exactly. This is not peculiar to the graviton. Photons travel at the speed of light for the same reason. What makes it significant in the gravitational context is that it provides a testable prediction, one that has, remarkably, already been tested. When two neutron stars merged in a cataclysmic collision detected by the LIGO and Virgo observatories on the 17th of August, 2017, the event was observed both in gravitational waves and in gamma rays. The gravitational wave signal and the gamma ray signal arrived at Earth within approximately 1.7 seconds of each other, after traveling approximately 130 million light years. 130 million light years of travel, and the difference in arrival time was less than 2 seconds. That constraint tells us that if the graviton has any mass, the resulting deviation from light speed is vanishingly small. The graviton's speed is consistent with the speed of light to within a few parts in 10 to the 15th. This is not a direct detection of a graviton, it is a measurement of gravitational waves, which are classical oscillations of space-time. But it is deeply consistent with the theoretical requirement that the graviton, if it exists, must be massless and must travel at exactly the speed of light. Now comes the property that most sharply distinguishes the graviton from every other known boson. Its spin. Spin is a quantum mechanical property with no precise classical analog. It is an intrinsic angular momentum carried by particles, a quantity that behaves mathematically like rotation, but is not actually a particle spinning around an axis in any ordinary sense. Electrons have spin 1/2, photons have spin 1, the Higgs boson has spin 0. Spin is a fundamental label that determines how a particle transforms under rotations in space, and it has deep consequences for the physics of any force mediated by that particle. For a spin 1 particle like the photon, there are two independent polarization states. Two ways the field can oscillate transverse to the direction of propagation. These correspond to what we call left circular and right circular polarization of light. The mathematics of spin 1 particles naturally produces forces that can be both attractive and repulsive, depending on the charges of the interacting particles. Two electrons, both negatively charged, repel each other through photon exchange. An electron and a positron, oppositely charged, attract each other. The spin of the boson and the structure of the force are connected. For the graviton, the spin must be 2. This is a requirement, not a guess. The argument comes from several directions simultaneously, and all of them point to the same number. The most direct argument comes from the polarization structure of gravitational waves. Gravitational waves have been detected by LIGO, and their properties measured with increasing precision since the first detection in 2015. Gravitational waves have two polarization states, just like electromagnetic waves. But the geometry of those polarization states is different. While light waves oscillate in patterns that look like a circle rotating, gravitational waves distort space in what are called plus and cross polarizations, patterns that look like a cross being stretched alternately in two perpendicular directions. The mathematical relationship between these polarization states, specifically the fact that rotating your viewpoint by 45 degrees maps one into the other, rather than the 90 degrees that would be expected for a spin 1 field, is the signature of a spin 2 field. This is not a subtle distinction. It is a precise, measurable geometric property of the wave. The observations confirm it. A second argument comes from consistency requirements in quantum field theory. If you try to build a consistent relativistic quantum theory of a massless spin 1 boson that couples universally to everything, coupling not just to electric charge or color charge, but to energy and momentum in general, which is what gravity does, you run into fundamental inconsistencies. The only massless boson that can couple universally to energy and momentum without violating the mathematical self-consistency of the theory is a spin 2 boson. This was established rigorously in the 1960s, and it is not a result that has been challenged. Spin 2 is the unique answer. A third argument comes from general relativity itself. When you expand the metric tensor, the mathematical object in general relativity that encodes the geometry of space-time around flat space-time, treating gravity as small perturbations on top of a flat background. The resulting wave equation describes a spin 2 massless field. The linearized version of general relativity, which is an excellent approximation when gravity is weak, is mathematically equivalent to the classical field theory of a massless spin 2 particle. Promoting this to a quantum theory and asking what particle emerges is what gives you the graviton. It emerges naturally from the structure of Einstein's equations. The spin 2 nature of the graviton has one consequence of overwhelming physical importance, and it explains something that might otherwise seem puzzling. Gravity is always attractive. Unlike electromagnetism, where like charges repel and opposite charges attract, there is no such thing as gravitational repulsion between ordinary masses. Everything with mass or energy attracts everything else with mass or energy. You cannot have negative gravitational charge the way you can have negative electric charge. Mass is always positive. This universal attraction is a direct consequence of spin 2. In quantum field theory, the character of a force, whether like sources attract or repel, depends on the spin of the mediating boson. For even spin, spin 0, spin 2, spin 4, like charges attract. For odd spin, spin 1, spin 3, like charges repel and opposite charges attract. Since the graviton has spin 2, which is even all masses attract all other masses, there are no negative masses in nature that could produce repulsion. The universal, exclusively attractive nature of gravity is not a coincidence. It is a theorem, derivable from the spin of the force carrier. So the theoretical profile of the graviton is now becoming clear. Massless, traveling at the speed of light, with spin 2, coupling universally to all energy and momentum. In these respects, it has a certain elegance, a logical necessity to it. Given that gravity exists and general relativity describes it correctly, a graviton with these properties is essentially inevitable if a quantum description of gravity exists at all. But now, we come to the property that transforms this elegant theoretical picture into an experimentalist nightmare. And it is the gravitational coupling constant. Every force has a coupling constant, a number that quantifies how strongly the force carrier interacts with matter. In quantum electrodynamics, the relevant coupling constant is the fine structure constant, denoted by the Greek letter alpha. Its value is approximately 1 divided by 137, roughly 0.007. This is a dimensionless number, meaning it has no units. It just is what it is, regardless of what system of measurement you use. It tells you the fundamental strength of the electromagnetic interaction. The fine structure constant is small, which is why perturbation theory works so well in quantum electrodynamics. You can expand calculations as a series in powers of alpha, and because alpha is much less than 1, higher order terms quickly become negligible. The calculations converge and produce the extraordinarily precise predictions that match experiments so beautifully. For the graviton, the relevant coupling constant is not a simple, dimensionless number like the fine structure constant. This is itself a signal of deep trouble, but we will come to that in time. In terms of the effective strength of the gravitational interaction between particles, the coupling is proportional to the energy of the particles involved, measured in units of the Planck mass divided by the Planck energy. And when you evaluate what this coupling looks like for ordinary particles at ordinary energies, you get a number that is almost incomprehensibly small. The gravitational coupling between two protons at the energies accessible to any particle accelerator ever built or ever likely to be built by human civilization is approximately 10 to the negative 38. Compare this to the fine structure constant of approximately 10 to the negative 2 for electromagnetism. The gravitational coupling is 36 orders of magnitude smaller. That 36 order of magnitude gap, the same gap that shows up in the hierarchy problem, now appears again here in the language of quantum field theory. The graviton does not just mediate a weak force, it mediates a force so weak that the probability of any graviton interaction at accessible energies is so small it is functionally indistinguishable from zero. To put this in terms you can hold in your mind, when a high-energy proton travels through the most sensitive particle detector ever built, the probability that it will interact via the electromagnetic force with the detector material is substantial. That is how the detector works. The probability that it will interact via the weak force in any given centimeter of travel is much smaller, but still measurable given sufficient numbers of particles. The probability that it will interact via a graviton exchange with any particle in the detector is so small that if you ran every particle accelerator on Earth simultaneously for the entire age of the universe, you would not expect to register even one gravitational interaction at the quantum level. This is not a limitation of current technology. It is not a problem that a bigger detector or a more sensitive instrument could solve in any straightforward sense. It is the physics of the coupling constant. The graviton simply does not interact with matter in any way that a practical detector could register. It is worth comparing this situation to the detection of neutrinos, because neutrinos also have an extremely weak coupling to matter, and yet we detect them. Neutrino detectors require enormous masses of material, massive underground tanks containing hundreds or thousands of tons of water or ice, or some other medium, because the cross-section for neutrino interactions is so small. Neutrinos produced in the sun pass through the entire Earth, as if it were almost completely transparent. A neutrino can travel through a light year of solid lead, and have roughly an even chance of passing through without interacting once. And yet we detect solar neutrinos, reactor neutrinos, and atmospheric neutrinos. We have built instruments sensitive enough to catch the rare events when a neutrino does interact. The graviton is not in this category. Its coupling is not merely much weaker than the neutrino coupling, it is incomprehensibly weaker. The cross-section, the effective area representing the probability of interaction for a graviton with a particle, is so small that the strategy of building a bigger detector, which works for neutrinos, completely fails for gravitons. You would need a detector of astronomical mass, literally. And even then, the detection rate would be essentially zero. A detector the mass of Jupiter, filled with the densest material imaginable, would not register a single graviton interaction over the lifetime of the universe at the energies associated with any known gravitational source. This has been worked out quantitatively by multiple physicists, and we will examine one of the most devastating of those arguments closely in due course. There's another way to see how unusual the graviton's coupling is by comparing it to its closest structural analog, the photon. Both the photon and the graviton are massless. Both travel at the speed of light. Both mediate long-range forces. Both are force carriers produced by quantum field theories, built on gauge symmetries. In many respects, they are structurally parallel. But the photon couples to electric charge. Not every particle has electric charge. Neutrinos, for example, are electrically neutral and do not interact via photon exchange at all, which is precisely why they're so difficult to detect. Dark matter, whatever it is, appears to be electromagnetically neutral. A particle simply being there in space does not guarantee it interacts with photons. The graviton couples to energy and momentum. Everything has energy and momentum. Every particle that exists, by virtue of existing, has mass or kinetic energy or both. There is no gravitationally neutral particle. There is no analog of electric neutrality for gravity. Everything couples to the graviton, without exception. In this sense, the graviton is more democratic than the photon. It interacts with literally everything that exists. But democracy at a coupling strength of 10 to the negative 38 is worse than irrelevance. It means the interaction is universal, but it also means the probability of any individual interaction occurring is so small that universality becomes cold comfort. You cannot exploit the universal coupling of the graviton the way you can exploit electromagnetic coupling to detect particles, because the coupling is too weak to produce detectable events at any accessible energy. The gluon offers a useful contrast from the opposite direction. The strong coupling constant, the equivalent of the fine structure constant for the strong force, is close to 1 at low energies. This is why the strong force is strong. A coupling constant near 1 means interactions are not rare. They happen readily. The probability of a quark absorbing or emitting a gluon inside a proton is not small. Gluons are exchanged constantly, furiously, in a dense quantum mechanical tangle inside every hadron. The strong force is strong precisely because its coupling constant is not suppressed. The gravitational coupling is at the opposite extreme. A coupling constant near 10 to the negative 38 means that graviton exchanges are not just rare, they are essentially non-existent at the energies of any particle or process we can produce or observe or wait for in any realistic scenario. The graviton is real in the same sense that a photon is real, if the theory is correct. But it is a particle that participates in the world so feebly that its individual quantum effects are completely invisible behind the classical average of enormous numbers of gravitons acting collectively. This is actually how we experience gravity at human scales. When you feel the pull of the earth beneath your feet, you are not feeling individual graviton exchanges. You are experiencing the cumulative effect of an unimaginable number of gravitons, every particle in your body exchanging gravitons with every particle in the earth simultaneously. The individual contributions each utterly negligible, but the collective sum producing the familiar one: gravitational acceleration that keeps you on the ground. Classical gravity, the smooth deterministic pull described by Newton, and the curved space-time described by Einstein, is an emergent phenomenon arising from the collective behavior of an astronomical number of gravitational quanta, each one interacting with near-zero probability. The classical description works so well precisely because we are averaging over such an enormous number of events that quantum fluctuations become completely invisible. In quantum electrodynamics, this same transition from quantum to classical is understood. Classical electromagnetic fields are made of photons. A radio wave is a coherent state of an enormous number of photons. The quantum granularity is invisible at the scales where classical electromagnetism applies. But the quantum structure can still be probed, because electromagnetic coupling is strong enough that individual photon interactions are physically measurable. You can detect a single photon. Photodetectors sensitive enough to register individual photon arrivals have existed since the early 20th century. The quantum nature of electromagnetism is experimentally accessible. For gravity, the quantum granularity may never be accessible. The coupling is too weak. The classical description is perfect at every scale where we can make measurements, and the quantum effects are so suppressed that they retreat to energy scales so extreme that no instrument built by any civilization operating under the laws of physics as we understand them could probe them directly. This is the core predicament. The graviton's theoretical profile is in many ways perfectly coherent. Massless, spin-2, traveling at light speed, coupling universally to all energy and momentum. The mathematics that demands its existence if gravity is quantized is rigorous and well understood. The particle makes sense on paper. It emerges naturally from taking general relativity and attempting to apply the same logic that produced the photon, the gluon, and the W and Z bosons. But the coupling constant, that single number describing how strongly it interacts with matter, is so small that the graviton inhabits a kind of physical ghost world. Present everywhere, coupling to everything, yet registering nothing in any detector we could ever build. Able to be inferred from the large-scale classical behavior of gravity, but impossible to catch in the act of doing what a quantum particle does, producing a discrete, individual, detectable interaction event. The photon was confirmed by detecting individual photon interactions. The W and Z bosons were confirmed by observing their decay products in particle colliders. The Higgs boson left its fingerprint in the statistical distribution of collision outcomes at the Large Hadron Collider. Every force carrier we have ever confirmed has made itself known through individual quantum interactions that an instrument could record. The graviton offers no such avenue. Its coupling is so weak that the path from theoretical necessity to experimental confirmation, a path that every other boson in the standard model has walked, is not merely difficult, it may be fundamentally permanently closed. Understanding exactly why that path is closed, and precisely how closed it is, requires going beyond the coupling constant alone to examine what a graviton detector would physically need to be. And that examination leads to one of the most remarkable and disturbing arguments in the history of physics. An argument that suggests the impossibility of single graviton detection is not just a practical limitation, but maybe a consequence of gravity itself. There's a thought experiment that every physicist who has seriously studied the graviton detection problem eventually encounters. And it has a way of ending conversations. Not because it is discouraging in some vague motivational sense, but because it is a precise, quantitative argument that arrives at a conclusion so stark it is difficult to absorb. The argument was laid out with characteristic clarity by Freeman Dyson, one of the great theoretical physicists of the 20th century, in a paper published in 2013. And what Dyson showed, working carefully through the numbers, is that the obstacle to detecting a single graviton is not technological. It is not a question of engineering or funding or cleverness. It is a question of whether the laws of physics themselves permit a graviton detector to exist. To appreciate the full weight of that argument, you need to understand what a detector actually does at the quantum level. When physicists talk about detecting a particle, they mean registering a single interaction event. A moment when the particle being detected transfers some of its energy or momentum to the detector material in a way that produces a measurable signal. For a photon detector, this might mean a single photon kicking an electron out of a metal surface in the photoelectric effect, or a photon being absorbed by a semiconductor and producing a tiny electrical pulse. For a neutrino detector, it means a neutrino occasionally, very rarely, interacting with a nucleus and producing a charged particle that travels through a medium fast enough to emit Cherenkov radiation, a faint blue glow that can be captured by photomultiplier tubes. In every case, the detection event is a real physical interaction, a transfer of energy, a change of state in the detector material, something concrete happening that can be recorded. For a graviton detector, the same logic applies in principle. A graviton would need to interact with something inside the detector, transfer energy or momentum to a particle or an atom or a nucleus, and that interaction would need to produce a signal distinguishable from background noise. The probability of any such interaction occurring depends on the cross-section, which is the quantum mechanical measure of how likely an interaction is. Think of the cross-section as an effective area that the target presents to the incoming particle. A large cross-section means interactions are probable. A small cross-section means they are rare. For gravitons, the cross-section is determined by Newton's gravitational constant, which encodes the gravitational coupling, divided by appropriate powers of the energy involved. When you evaluate this for a graviton with the energy of a typical astrophysical source, say a graviton produced by the collision of two neutron stars, the cross-section comes out to something in the range of 10 to the negative 65 square centimeters, or smaller. To give that number context, the cross-section for a neutrino interaction with a proton at the same energy scale is roughly 10 to the negative 42 square centimeters. the graviton cross-section is smaller than the neutrino cross-section by more than 20 orders of magnitude. More than 100 billion times smaller. The neutrino, which passes through a light year of lead, with roughly even odds of not interacting once, is a gregarious socialite compared to the graviton. This cross-section determines how much detector material you would need to register a single interaction. For neutrino detection, the logic is brutal but not hopeless. Make the detector enormous. The Ice Cube Neutrino Observatory at the South Pole is a cubic kilometer of Antarctic ice, instrumented with over 5,000 light sensors, and it detects roughly 100,000 neutrino events per year. Scale up the detector and you get more events. The cross-section is small but finite, and non-zero in a way that allows a sufficiently large detector to compensate. For a graviton, you apply the same logic. You take the cross-section, you estimate the flux of gravitons arriving at Earth from some astrophysical source, and you calculate what mass of detector material you would need to accumulate enough interaction probability to expect even one event per year. The answer is not a large detector. It is not a very large detector. It is not an absurdly large detector. The answer is a detector whose mass exceeds the mass of Jupiter by a significant margin. And even that extraordinary figure assumes a graviton source of roughly the strength of 2 merging neutron stars. The most powerful gravitational wave events known, bathing the detector continuously. A detector, the mass of Jupiter. This is not a rhetorical exaggeration, it is a calculation, and it is where Dyson's argument begins to close in on its devastating conclusion. A detector the mass of Jupiter concentrated in one place is not a detector. It is a planet. A very massive planet. And a very massive planet, depending on how its mass is distributed and what it is made of, has a tendency to do what massive things do: collapse under its own gravity. Jupiter itself falls far short of the mass needed to become a brown dwarf, a failed star requiring approximately 13 times its actual mass before deuterium fusion could ignite in its core. A detector significantly more massive than Jupiter, dense enough to present a reasonable interaction probability to incoming gravitons, would not be an inert slab of instrumented material. It would be a self-gravitating body with a complex internal structure determined by the physics of matter under extreme pressure. But here is the deeper point. The cross-section for graviton interaction scales with the energy of the graviton. Higher energy gravitons have slightly larger cross-sections and are therefore slightly easier to detect in principle. To maximize your detection probability, you want the highest energy gravitons you can find, which means the most violent and energetic astrophysical sources possible. But a detector massive enough to intercept even one such graviton per year must be so massive that it exists under conditions of extreme self-gravity. And a detector that is both extremely massive and sensitive to gravitational disturbances, which a graviton detector must be, by definition, faces a fundamental problem. The gravitational noise produced by the quantum fluctuations of the detector's own gravitational field will swamp any signal from an incoming graviton. Dyson's specific argument runs as follows. A graviton detector must be sensitive enough to register the disturbance caused by the absorption of a single graviton. The energy deposited by a single graviton is extraordinarily small. For a graviton of astrophysical origin, it is roughly comparable to the energy of a very low frequency photon. To detect this tiny disturbance, the detector must have extraordinarily low internal noise. The dominant source of noise in any mechanical system is thermal noise, the random jiggling of atoms due to their thermal energy. To suppress thermal noise to the level required to detect a single graviton, you would need to cool the detector to temperatures approaching absolute zero. And even then, the 0-point quantum mechanical fluctuations of the atoms remain. But there is a deeper noise source that cooling cannot eliminate. A detector of the mass required to have any reasonable interaction probability with gravitons will itself produce gravitational radiation, gravitons, through the quantum fluctuations of its own constituent particles. The gravitational noise emitted by the detector is not a background effect that clever shielding can eliminate. It is produced by the same physical processes you are trying to detect. And Dyson's calculation shows that for any detector massive enough and sensitive enough to detect an incoming graviton, the noise level produced by the detector's own quantum fluctuations is larger than the signal level from the incoming graviton. The signal-to-noise ratio is less than 1. You cannot, even in principle, distinguish a genuine graviton detection event from the gravitational fluctuations of the detector itself. This is not an argument about imperfect engineering. It is an argument that the detector, by virtue of having the mass necessary to interact with gravitons at all, necessarily produces more gravitational noise than the signal it is trying to measure. The very property that makes it a detector, its mass, makes it blind. You cannot win this game by making the detector bigger, because making it bigger increases both the signal probability and the noise level. And the noise always wins. The ratio does not improve with scale. Dyson was careful to note that his argument does not constitute a rigorous proof that graviton detection is impossible under all conceivable circumstances. Physics is full of surprises, and a sufficiently clever configuration might evade some of these constraints. But the argument is quantitative and specific, and no credible counter-argument has been published that identifies a physical mechanism capable of defeating it. The conclusion that single graviton detection is not merely difficult, but physically impossible, ruled out by the internal consistency of the laws of physics, rather than by the current limitations of technology, is taken seriously by the community of physicists who have examined it. This brings us to a distinction that is essential and frequently misunderstood, because there is a version of this story that sounds like a refutation of everything just said. In September of 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time, produced by the merger of two black holes approximately 1.3 billion light-years away. The signal, a tiny oscillation in the length of LIGO's 4-kilometer arms lasting a fraction of a second, represented a change in distance of roughly 1,000th of the diameter of a proton. It was one of the most precise measurements ever made in the history of science. Since that first detection, LIGO and its partner observatory Virgo have detected dozens of gravitational wave events, including black hole mergers, neutron star mergers, and mixed events involving both types of objects. The era of gravitational wave astronomy has arrived, and it is producing remarkable science. Does this mean we have detected gravitons? No. The distinction matters enormously, and understanding it is central to understanding what the graviton problem actually is. Gravitational waves are a classical phenomenon. They are oscillations in the curvature of space-time, ripples in the geometry of the universe that propagate outward from violent astrophysical events at the speed of light. They are predicted by general relativity, which is a classical theory containing no quantum mechanics whatsoever. Their existence was inferred by Einstein in 1916, 1 year after he published the field equations. They are to the gravitational field what radio waves are to the electromagnetic field. Classical wave phenomena that can be described entirely without reference to quantization. When LIGO detects a gravitational wave, it is measuring a collective, classical disturbance in space-time involving a number of gravitons so staggering that the quantum granularity is completely invisible. Consider the energy carried by the gravitational wave signal from that first black hole merger. 2 black holes, each roughly 30 times the mass of the Sun, spiraling together and merging in a fraction of a second. The peak power output of that event exceeded the combined luminosity of all the stars in the observable universe by a factor of roughly 50. The total energy radiated in gravitational waves was equivalent to approximately 3 solar masses, 3 times the mass of the entire Sun, converted directly into gravitational wave energy in under a second. In the language of gravitons, this represents a number of individual gravitons so large it is essentially uncountable. The gravitons in the LIGO signal are not individual quanta producing discrete events. They are an ocean of quanta, and the wave is an emergent classical property of that ocean. LIGO is sensitive to the wave. It is not sensitive to, and was not designed to detect, and cannot detect, individual gravitons. The analogy to electromagnetism is precise and clarifying. A radio receiver detects radio waves, classical electromagnetic oscillations. It does not detect individual photons. To detect individual photons, you need a completely different type of instrument operating on completely different physical principles, sensitive to individual quantum interaction events rather than continuous wave oscillations. Both types of detection are possible for electromagnetism because the photon's coupling is strong enough that individual photon interactions can be made to produce measurable signals. For gravity, the classical wave detection is achievable, as LIGO has magnificently demonstrated. The individual quantum detection, the graviton equivalent of a photomultiplier tube clicking in response to a single photon, is the step that Dyson's argument suggests may be physically forbidden. This distinction also clarifies a related point about what LIGO has and has not confirmed. The detection of gravitational waves is consistent with the existence of gravitons. If gravitational waves exist and are quantized, then gravitons exist. But detecting waves does not confirm quantization, just as detecting radio waves does not confirm the photon. The quantum nature of the electromagnetism was confirmed by discrete photoelectric events, by the observation that energy is transferred in lumps rather than continuously. The quantum nature of gravity would require observing gravitational energy transferred in discrete lumps, individual graviton absorption events, and that is precisely what has not been done and may never be done. There is a further dimension to this problem that goes beyond detector design and into the fundamental energy scales of physics. Even setting aside the detection problem entirely, there is a scale at which gravitational quantum effects would become naturally significant. A scale at which the graviton's physics would no longer be suppressed into irrelevance by the smallness of the coupling. This is the Planck scale, named after Max Planck, who in 1899 identified a natural system of units constructed from the fundamental constants of nature: the speed of light, Planck's constant, and Newton's gravitational constant. The Planck length is approximately 1.6 times 10 to the negative 35 meters. The Planck time is approximately 5.4 times 10 to the negative 44 seconds, the time it takes light to travel one Planck length. The Planck mass is approximately 2.2 times 10 to the negative 8 kilograms, which sounds small by everyday standards, but is enormous by particle physics standards. It is equivalent to an energy of approximately 1.2 times 10 to the 19th giga-electron-volts. This is called the Planck energy. At the Planck scale, gravitational quantum effects are not suppressed. The coupling constant that is so catastrophically small at ordinary energies grows with energy and becomes of order 1 at the Planck scale. This is where quantum gravity effects dominate. This is where the graviton is no longer a ghost, where its interactions become frequent and significant, and the quantum nature of space-time itself becomes physically relevant and cannot be ignored. The Large Hadron Collider, the most powerful particle accelerator ever built, achieves collision energies of approximately 13.6 tera-electron-volts, 13.6 times 10 to the 12th electron-volts. The Planck energy is approximately 1.2 times 10 to the 28th electron-volts. The ratio between the Planck energy and the maximum collision energy of the LHC is roughly 1 quadrillion 10 to the 15th. The LHC is 15 orders of magnitude away from the Planck scale. To reach the Planck energy with a circular particle accelerator using current magnet technology, you would need an accelerator ring roughly 3 times 10 to the 19th meters in circumference. That is approximately 3,000 light years. Not 3,000 kilometers, not 3,000 miles. 3,000 light years of continuous precision magnetic infrastructure, stretching across a distance 700 times greater than the gap between our Sun and the nearest neighboring star system, and covering roughly 3% of the Milky Way's entire diameter from edge to edge. You would need an accelerator covering roughly 3% of our entire galaxy's diameter to directly probe the energies at which graviton physics becomes experimentally accessible. This is not a number that improves with incremental technological progress. It does not shrink by a factor of 10 with the next generation of accelerators. The gap between the highest energies human technology can produce and the Planck energy, where quantum gravity becomes relevant, is so enormous that it cannot be bridged by any extrapolation of known engineering. Even proposals for truly exotic and futuristic accelerator concepts, plasma Wakefield accelerators, laser-driven schemes, techniques not yet imagined, face this gap. Physics does not forbid better accelerators, but the gap to the Planck scale is not a technological challenge in any ordinary sense. It is a fundamental mismatch between the scale of human engineering and the scale at which nature has chosen to make gravity quantum mechanical. There is a further layer of subtlety here that deserves careful attention, because it sometimes leads to confusion. The Planck scale is often described as the scale at which quantum gravity effects become important. And this is true in the sense that it is where the gravitational coupling reaches order 1. But there is another way to think about what the Planck scale represents. It is the scale at which the Schwarzschild radius of a particle, the radius of the black hole you would create by compressing that particle's mass energy into a small enough volume, becomes comparable to its quantum mechanical de Broglie wavelength. In other words, it is the scale at which you cannot localize a particle more precisely without the act of localization itself creating a black hole. This is a profound and disturbing realization. In ordinary quantum mechanics, you can in principle measure the position of a particle to arbitrary precision, at the cost of giving it an arbitrarily large momentum uncertainty. There is no fundamental lower limit to how precisely you can localize something, but at the Planck scale, localizing a particle to its Planck length scale quantum uncertainty would require concentrating energy equivalent to the Planck mass into a Planck length volume, and at that density, the concentrated energy would itself curve spacetime so severely that a black hole would form. The act of measurement would create a black hole. The black hole would absorb the particle and the measuring apparatus simultaneously. The measurement would be destroyed by its own success. This suggests that the Planck length is not merely a very small distance that we lack the technology to probe. It may be the smallest meaningful distance, a fundamental limit built into the structure of physics itself, below which the concept of distance loses meaning because the geometry of space-time becomes too violently uncertain to define any notion of location. If this is correct, then the question of what happens to the graviton at sub-Planck scales is not a question that has an answer, not because we lack the tools to find the answer, but because the question may not be well formed. All of this converges on a picture of extraordinary bleakness from the experimental perspective. The graviton is theoretically required. Its properties are sharply constrained by well-understood physics. Its mass must be essentially zero. It must travel at the speed of light. It must have spin 2. It must couple to all energy and momentum. All of these properties are internally consistent, and the classical predictions that follow from assuming the graviton exists, the existence of gravitational waves, their speed, their polarization properties, have been confirmed by observation. But the quantum predictions, the ones that would specifically confirm the graviton's existence as a quantum particle rather than as a label we attach to the classical gravitational field, require detecting individual graviton interactions. And the cross-section for individual graviton interactions is so small, and the mass required of any detector sensitive enough to accumulate reasonable interaction. Probability is so large, and the gravitational noise produced by any such detector is so overwhelming, that the detection appears to be not merely practically impossible, but forbidden by the self-consistency of general relativity and quantum mechanics applied together. LIGO and Virgo have opened a new window on the universe. They have confirmed the existence of gravitational waves and ushered in the era of multi-messenger astronomy, the ability to observe catastrophic events using both light and gravitational radiation simultaneously, triangulating not just the energy released, but the geometry, the composition, the physics of the most violent events in the cosmos. This is a genuine and profound scientific achievement, one that will produce discoveries for generations. But it is not, and cannot be, a detection of the graviton as a quantum particle. It is the detection of the classical wave that a vast sea of gravitons collectively produces, as far removed from individual graviton detection as the hum of a power line is from the detection of an individual photon. The graviton therefore occupies a position unlike anything else in physics. LIGO has given us something genuinely extraordinary, a new sense by which to perceive the universe, capable of detecting the most violent events in the cosmos across 1 billion light-years of space. But what LIGO hears is the roar of an ocean, not the click of a single drop. The transition from detecting gravitational waves to detecting gravitons is not a matter of upgrading a detector or refining a technique. It is a transition between two entirely different regimes of physics, separated by the Dyson argument on one side and the Planck scale gap on the other, with neither obstacle yielding to any engineering we can conceive of. What remains is a question that runs deeper than detection, deeper than energy scales, and deeper than any engineering constraint. It is a question about the internal consistency of our best understanding of nature. The graviton, if it exists, belongs to a theory we do not yet possess. Not because the mathematics has not been attempted, it has, in extraordinary depth and detail, by generations of gifted physicists working across many decades. But every attempt to write down the full quantum theory of gravity has encountered a specific kind of failure, unlike the failures encountered by other theories. It is a failure in which the equations do not merely give the wrong answer, but refuse to give any answer at all, collapsing instead into an escalating cascade of undetermined parameters, each one demanding to be fixed by experiment before any prediction can be made, each one spawning new undetermined quantities in turn. That failure, its origin, and its deep implications for the nature of space and time is the heart of what this problem actually is. Everything described so far, the weakness of the gravitational coupling, the theoretical profile of the graviton, the impossibility of detecting individual gravitons with any physically realizable instrument, all of it is, in a certain sense, peripheral to the deepest problem. Those are consequences of gravity's strangeness. They are symptoms. The disease itself lives in the mathematics. And the mathematics, when physicists have seriously attempted to build a quantum field theory of gravity around the graviton, does not merely produce difficult answers. It produces no answers at all. The equations break. Not in the way that an approximation breaks when pushed beyond its domain of validity. In the way that a calculation breaks when it produces infinity. When the answer to a physically meaningful question is not a large number or a small number, but a number that is literally without limit, diverging toward infinity in a way that cannot be removed, cannot be cancelled, cannot be absorbed into a redefinition of physical quantities. The theory stops being a theory. It becomes a collection of symbols that point at nothing. To understand why this happens, you need to understand what renormalization is and why it works for the other forces, but catastrophically fails for gravity. In quantum field theory, calculations are performed using a technique called perturbation theory. The idea is that if a coupling constant is small, if the force is relatively weak, then you can compute physical quantities as a series of increasingly complex contributions, each one smaller than the last by a factor related to the coupling constant. The leading term gives you the dominant contribution. The next term gives you a small correction. The term after that gives a smaller correction still. You sum the series and get an answer that matches experiment extraordinarily well, provided the coupling constant is genuinely small enough for the series to converge rapidly. This approach works magnificently for quantum electrodynamics. The fine structure constant, the electromagnetic coupling, is approximately 1 divided by 137. Small enough that the perturbative series converges rapidly. Each successive correction is smaller than the previous by roughly a factor of 137. You need only compute the first few terms to get predictions accurate to 10 decimal places. But when you try to perform these perturbative calculations in quantum field theory, you discover that individual terms in the series involve integrals over the momenta of virtual particles. These are particles that appear and disappear within the quantum mechanical uncertainty permitted by the Heisenberg principle. Short-lived excitations of the quantum field that mediate the force. The integrals over their momenta run from 0 to infinity, because there is no upper limit on how much momentum a virtual particle can carry, at least not in the naive formulation of the theory. And many of these integrals, when evaluated directly, diverge. They produce infinity. This is not a crisis unique to gravity. It appears in quantum electrodynamics as well. The self-energy of the electron, the energy contribution from the electron interacting with its own electromagnetic field through virtual photon exchange, is formally infinite in a naive calculation. This alarmed the physicists who first encountered it and seemed to suggest the theory was fundamentally broken. But the infinities in quantum electrodynamics can be tamed through a procedure called renormalization. The essential idea is that the parameters appearing in the equations of the theory, the mass and charge of the electron, for example, are not the same as the physical, measurable mass and charge of the electron. The bare parameters that appear in the Lagrangian are abstract mathematical quantities that include contributions from all the virtual processes. The physical parameters are what you actually measure in the laboratory. Renormalization is a procedure that absorbs the infinities into a redefinition of the bare parameters. You replace the infinite bare mass with the finite physical mass, absorb the infinity into the definition, and what remains after this. Substitution is a finite, physically meaningful prediction. The infinities cancel between the bare parameters and the loop corrections, leaving a finite residue that is the actual prediction of the theory. The crucial requirement for this procedure to work is that the infinities must be of the right form. Specifically, they must be absorbable into a finite number of parameters. In quantum electrodynamics, there are only a few parameters: the electron mass, the electron charge, and a normalization of the field, and the infinities that appear at every order of perturbation theory are all of a form that can be absorbed into redefinitions of these few parameters. No matter how many loop diagrams you compute, no new types of infinity appear that would require introducing new parameters not already present in the original theory. The theory is self-contained. It needs only the parameters it started with. This is what physicists mean when they call a theory renormalizable. It can absorb its own infinities with a finite number of counterterms. For gravity, this procedure fails in the most complete way imaginable. When you compute quantum corrections to gravitational scattering, when you draw the Feynman diagrams that represent virtual graviton exchange at higher and higher orders of perturbation theory, new types of infinities appear at each order that cannot be absorbed into the original parameters of the theory. At one loop, the first order of quantum correction, you can absorb the infinities if you add two new parameters to the theory. But at two loops, new infinities appear that require additional new parameters. And at three loops, more new parameters are needed. At every order of perturbation theory, the infinities multiply and new undetermined parameters must be introduced to absorb them. After infinitely many orders of perturbation theory, you would need infinitely many free parameters, infinitely many physical quantities that must be measured and fed into the theory from outside before any prediction can be made. A theory with infinitely many free parameters is not a theory. It has no predictive power. It can accommodate any experimental result by adjusting its parameters appropriately, which means it predicts nothing. It explains nothing. It is an elaborate accounting system, not a description of physical reality. This is the technical statement of the non-renormalizability of quantum gravity. The groundwork was laid in the 1970s by Gerard 't Hooft and Martinus Veltman, who had previously shown that the electroweak theory is renormalizable, and who later shared the Nobel Prize in Physics for that work, when they demonstrated that quantum gravity coupled to matter fields requires counterterms not present in the original Lagrangian. But the definitive proof arrived in 1985, when Mark Goroff and Augusto Sagnotti completed the extraordinarily laborious two-loop calculation for pure quantum gravity without any matter fields, and found a genuine, non-removable divergence that no redefinition of existing parameters could absorb. This result was independently confirmed by Anton van der Ven in 1992. Together, these calculations close the case. The graviton, as the carrier of a non-renormalizable interaction, cannot be the basis for a consistent perturbative quantum field theory of the same type that works for the other forces. The root cause of this non-renormalizability is deeply connected to a feature of the gravitational coupling mentioned earlier, the fact that it is not dimensionless. Newton's gravitational constant, which controls the strength of gravity, has dimensions of length cubed divided by mass times time squared in standard units, which translates to inverse mass squared in natural units, where the speed of light and Planck's constant are set to 1. This dimensionful nature of the coupling is fatal for renormalizability. When a coupling constant is dimensionless, as the fine structure constant is, the coupling does not change the dimensional analysis of loop integrals in a way that introduces new types of divergences at higher orders. The same finite set of counterterms absorbs all the infinities, but when the coupling constant has dimensions of inverse mass squared, every additional loop brings in additional powers of the coupling constant, additional inverse powers of mass squared, and to compensate dimensionally, the corresponding integrals must be more divergent. Each loop order introduces a new degree of divergence, requiring new counterterms, and the counterterms at one order generate new infinities at the next. The cascade is endless and unstoppable. The dimensionful coupling constant ensures that quantum gravity generates its own infinities without limit. This is why the Planck scale, introduced earlier, is not merely the scale at which gravitational quantum effects become strong. It is the scale at which the perturbative expansion itself breaks down completely, where the coupling constant multiplied by the square of the energy reaches order 1, and every term in the perturbative series becomes equally important. Below the Planck scale, perturbation theory is technically applicable, but produces predictions of no physical interest because gravity is negligible. Above the Planck scale, perturbation theory is inapplicable because it has broken down. The theory has no domain in which it is both relevant and mathematically consistent. The graviton, as a perturbative quantum field theory, simply does not exist in any meaningful sense. Faced with this situation, theoretical physicists over the past several decades have pursued two fundamentally different strategies for constructing a consistent theory of quantum gravity. Neither has produced a confirmed physical theory. Both remain research programs rather than established science, and both make predictions that are extraordinarily difficult or impossible to test with any foreseeable technology. but they represent the most serious current attempts to answer the question of what a quantum theory of gravity actually is. The first and most extensively developed approach is string theory. The core idea of string theory is that the fundamental entities of nature are not point-like particles, but tiny one-dimensional objects, strings, whose length is comparable to the Planck length. Different vibrational modes of these strings correspond to different particles. A string vibrating in one mode is an electron. The same string vibrating in a different mode is a photon. And crucially, there is always a vibrational mode corresponding to a massless spin-2 particle. The graviton emerges automatically from the spectrum of vibrating strings. It is not inserted by hand. It is not a separate hypothesis. It is simply there as an inevitable consequence of the consistency conditions of the theory. This is the most striking feature of string theory from the graviton perspective. The graviton is not added to string theory, it is derived from it. Any consistent string theory necessarily contains a massless spin-2 excitation, and a massless spin-2 excitation necessarily mediates a long-range force with the properties of gravity. String theory predicts gravity. This was first recognized in 1974 when Joel Shirk and John Schwartz identified the massless spin-2 string excitation as the graviton, and it was the first superstring revolution of 1984 when Green and Schwartz demonstrated a crucial anomaly cancellation that transformed string theory into a candidate theory of everything. The enormous excitement that followed has not entirely subsided, though 4 decades of subsequent work have produced no experimental confirmation. String theory also resolves the non-renormalizability problem, at least in principle. The replacement of point-like particles with strings of finite length effectively smooths out the short-distance behavior of the theory. The divergences that plague point-particle quantum field theory arise because you are integrating over contributions from virtual particles with arbitrarily short wavelengths, arbitrarily high momenta, and these short-distance contributions produce infinities. With strings of finite length, there is a natural ultraviolet cutoff at the string scale, roughly the Planck scale. The integrals are automatically regulated. The infinities do not appear. String theory is perturbatively finite in a way that point-particle quantum gravity is not. This sounds like exactly the solution needed, and it may be. But string theory carries with it a set of features and requirements that have made its confirmation essentially impossible to date, and which raise deep questions about whether it is physics or mathematics. String theory requires additional spatial dimensions. The most studied versions of string theory are mathematically consistent only in 10 or 11 space-time dimensions. 10 or 11, not the 4 we observe. The 6 or 7 extra spatial dimensions must be compactified, curled up into shapes so small they are invisible at any accessible energy scale. The geometry of these extra dimensions determines the low-energy physics. Different compactifications produce different particles, different coupling constants, different values of fundamental parameters. The number of distinct consistent compactifications is staggeringly large. Estimates range up to 10 to the 500. This enormous landscape of possible string theory vacua is called the string landscape, and it raises a profound question. With so many possible configurations, each corresponding to a different low-energy physics, how do you predict which one corresponds to the universe we actually live in? Without a principle that selects a unique vacuum String theory does not make specific predictions about particle masses, coupling constants, or the structure of the standard model. It accommodates many possible universes, which some physicists regard as a feature and others regard as a fatal flaw. There is a third development in quantum gravity research that deserves serious attention here, not because it is a complete theory, but because it has provided something that neither string theory in its full complexity nor loop quantum gravity has yet delivered in any broad sense. A controlled, mathematically precise setting in which certain quantum gravity calculations can actually be performed and checked. This is the anti-de Sitter space conformal field theory correspondence, known as ADS/CFT, proposed by the physicist Juan Maldatina in 1997. The central claim of ADS/CFT is both simple to state and extraordinarily deep in its implications. It asserts that a quantum theory of gravity, specifically string theory, formulated in a particular type of spacetime called anti-de Sitter space, which is a spacetime with a specific negative curvature, is exactly mathematically equivalent to a quantum field theory without gravity formulated on the lower dimensional boundary of that spacetime. The gravity theory lives in the bulk. The non-gravitational quantum field theory lives on the surface that encloses it. Neither is more real than the other. They are two descriptions of the same physical system, related by a precise mathematical dictionary that translates quantities in one theory into quantities in the other. This equivalence is called a duality, and it is one of the most remarkable and productive ideas in theoretical physics over the past 3 decades. Its significance for quantum gravity is profound. The quantum field theory on the boundary is an ordinary quantum field theory, the kind physicists know how to handle mathematically, without the non-renormalizability problems that plague attempts to quantize gravity directly. When the gravity in the bulk is strongly curved and quantum effects are large, precisely the regime where standard perturbative quantum gravity breaks down completely. The boundary theory is weakly coupled and calculations are tractable. A DS/CFT translates an intractable gravitational calculation into a manageable quantum field theory calculation. It provides, for the first time, a setting where questions about quantum gravity can be asked and answered with mathematical rigor rather than formal manipulation of divergent series. What has ADS/CFT actually confirmed about the graviton specifically? The graviton appears in the ADS/CFT framework as a particular operator in the boundary field theory. A spin-2 excitation that corresponds, through the dictionary, to a massless spin-2 particle propagating in the bulk. The consistency of the correspondence requires this identification, and calculations performed using the duality reproduce the expected gravitons, scattering amplitudes in the appropriate limits. This does not constitute a detection of the graviton. It does not resolve the non-renormalizability problem in full generality. Anti-de Sitter space is not the spacetime we live in. Our universe as a positive cosmological constant, not a negative one, and extending ADS/CFT to de Sitter space or to flat spacetime remains an active and unsolved research problem. But ADS/CFT has demonstrated something crucial: that a mathematically consistent quantum theory containing gravity and containing objects that behave like gravitons can exist. The non-renormalizability of perturbative quantum gravity does not necessarily mean quantum gravity is impossible. It may mean that the perturbative approach is simply the wrong tool. that the correct description of quantum gravity is non-perturbative and holographic in a way that ordinary quantum field theory in 4 dimensions is not. This is a genuine insight. It does not complete the theory. It does not tell us whether the graviton is fundamental or emergent. It does not give us a description of quantum gravity in the universe we actually inhabit. But it shifts the question from whether a consistent quantum theory of gravity can exist to what form that theory takes and how to extract from it the physics of the universe we observe. The second major approach to quantum gravity is loop quantum gravity, which takes a different starting point and arrives at a different picture with different virtues and different problems. Loop quantum gravity does not attempt to unify gravity with the other forces. It focuses exclusively on quantizing general relativity directly, using a reformulation of Einstein's equations in terms of variables that are more amenable to quantization. The central result of loop quantum gravity is that space itself, not space as a backdrop for physics, but the geometric structure of space, is quantized. Area and volume are not continuous quantities that can take any value. They come in discrete lumps, the smallest of which are a Planck length scale. Space is not smooth, it is granular. At the Planck scale, the geometry of the universe is a quantum object described by what are called spin networks, graphs whose edges and nodes carry quantum numbers encoding the discrete areas and volumes of spatial regions. In loop quantum gravity, the graviton emerges as a particular type of excitation of this quantized spacetime, a ripple in the spin network that, at large scales, looks like a gravitational wave. The theory avoids the infinities of perturbative quantum gravity because it is not a perturbative theory. It is formulated non-perturbatively. It describes the full quantum geometry rather than treating quantum fluctuations as small corrections on top of a classical background. This is both its strength and its weakness. It is a strength because the infinities that arise in perturbative approaches are absent. It is a weakness because the non-perturbative formulation makes calculations extraordinarily difficult, and the recovery of smooth classical spacetime from the discrete spin network structure at large scales is technically challenging and not yet fully resolved. Both string theory and loop quantum gravity predict the existence of gravitons, though in different senses and with different structures. Both predict that spacetime at the Planck scale is radically different from the smooth continuum we observe. Both make some predictions that are potentially testable in principle, though not with any technology currently available or likely to be available in the foreseeable future. And both remain genuinely open questions about whether they correctly describe nature. What is important here is that neither of these theories is confirmed. Neither has produced a prediction that has been verified by experiment in a way that rules out alternatives. String theory's most distinctive predictions, supersymmetric partners of known particles, extra dimensions, the specific structure of the string landscape, have not been confirmed at the LHC or anywhere else. Loop quantum gravity makes predictions about the discrete structure of spacetime that would, in principle, affect the propagation of very high-energy photons over cosmological distances, but the predicted effects are at or below the current sensitivity of gamma-ray telescopes. Both theories are mathematically sophisticated and internally coherent in important ways. Both have attracted extraordinary intellectual talent and produced deep mathematical insights. But neither has crossed the threshold from theoretical possibility to physical confirmation. The graviton therefore sits in a peculiar position relative to both. It is demanded by both theories. Its classical properties, mass, spin, speed, coupling, are fixed by well-established physics independently of either. But the deeper quantum theory that would give the graviton its full meaning, that would tell us not just what properties it must have, but how space-time itself behaves at quantum scales, why gravity is so weak, how the graviton fits with the other forces into a unified framework. That theory does not yet exist in any confirmed form. This brings us to a question that deserves to be asked plainly. Does the graviton have to exist? Is it possible that gravity is simply not quantized? That it is a fundamentally classical phenomenon in a universe where everything else is quantum mechanical? This possibility is more uncomfortable than it might initially sound. If gravity is classical and quantum mechanics describes everything else, then the universe has two incompatible frameworks that must somehow coexist. This is not just aesthetically unsatisfying, it leads to physical inconsistencies. If you allow a classical gravitational field to interact with quantum matter that exists in superpositions of different states, then the gravitational field must respond to the quantum expectation value of the mass distribution. But this produces predictions that violate either quantum mechanics or general relativity when pushed to extremes. You cannot consistently marry a classical gravitational field to a fully quantum matter sector without one framework or the other breaking down. The universe appears to demand that gravity be quantum mechanical if the rest of physics is quantum mechanical. The graviton must exist, or something must replace the entire framework within which that demand is made. There is one more aspect of the graviton problem that reveals something even more disquieting about the nature of the physical world. In every other quantum field theory, the force-carrying boson mediates interactions between particles against a fixed background spacetime. The photon travels through space, the gluon acts within space, the W and Z bosons propagate through the spacetime geometry provided by general relativity at low energies. Space and time are the arena. The particles are the actors. The arena and the actors are separate things. For the graviton, this separation collapses. The graviton does not travel through spacetime. It is an excitation of spacetime. It is not an actor on the stage. It is a ripple in the fabric of the stage itself. And this means that the entire conceptual framework of quantum field theory, which assumes a fixed, classical background spacetime over which quantum fields propagate, is fundamentally inappropriate for describing the graviton. Every other quantum field theory we have ever written down is, at some level, defined relative to a background. Even in general relativity, calculations of quantum effects in curved spacetime treat the geometry as fixed and ask how quantum fields behave in that fixed geometry. This works as long as the quantum fields do not significantly back-react on the geometry. But a quantum theory of the graviton is not a theory of a quantum field on a background spacetime. It is a theory of quantum spacetime itself. The arena is part of the dynamics. There is no fixed background to expand around, no fixed geometry to use as a reference. The geometry is itself a quantum variable, fluctuating and uncertain. What does it mean for space and time to exist in a superposition of different geometries? What does it mean for the distance between 2 points to be quantum mechanically uncertain? What is causality, the principle that causes precede effects in time, when the temporal ordering of events is itself subject to quantum uncertainty? These are not rhetorical questions designed to convey the impressiveness of the problem. They are genuine open questions that do not have answers within the current framework of physics. Attempts to define a quantum theory of space-time, whether through string theory's extended objects, loop quantum gravity's spin networks, or other approaches including causal dynamical triangulations, causal set theory, and asymptotic safety, all run into the fundamental challenge that the language we use to describe quantum systems assumes the existence of a background space-time within which the system is defined. Quantum gravity requires a theory that is background independent in a deep sense, a theory that does not assume the existence of any fixed geometry, but derives the emergence of smooth space-time as a low-energy approximation to something more fundamental. What that more fundamental thing is, no one knows. Whether it involves gravitons as the quanta of the emergent gravitational field, or whether at the deepest level the graviton is merely an effective description valid only well below the Planck scale, is a question that remains entirely open. The graviton may be a fundamental particle in the same sense that the photon is fundamental, or it may be an emergent, approximate concept, a useful label for the low-energy excitations of a more fundamental structure that has no particle description at all. The photon analogy, compelling as it is, may be misleading precisely because it imports the assumptions of ordinary quantum field theory into a domain where those assumptions have never been validated. What the story of the graviton ultimately reveals is the precise location of the most profound boundary in all of physics. On one side of that boundary, we have two frameworks of incomparable success. Quantum field theory and the Standard Model describe every particle, every force except gravity, every laboratory experiment, every particle accelerator result, every phenomenon from atomic spectra to the Higgs boson with precision that has never been matched by any other scientific framework in human history. General relativity describes gravity, space-time, black holes, gravitational waves, the expansion of the universe, the Big Bang cosmology, and the large-scale structure of the cosmos with equal extraordinary precision. Between them, these two frameworks describe essentially everything that happens in the observable universe. There is no confirmed experimental result that either framework cannot account for within its domain of applicability. On the other side of that boundary, the two frameworks are mutually incompatible. They cannot both be fundamental. They make contradictory assumptions about the nature of reality. Quantum mechanics demands that physical quantities be uncertain and probabilistic. General relativity demands that space-time be smooth and deterministic. At the energies accessible to human technology, the two frameworks never need to interact directly, and the inconsistency is invisible. But logically, mathematically, at the level of foundations, the inconsistency is absolute. The universe cannot be simultaneously described by two incompatible frameworks, unless one or both of them is an approximation to something deeper. The graviton stands at this boundary. It is what general relativity predicts must exist if the rest of physics is correct. It is what quantum field theory requires if gravity is to be described within its framework. It is the particle whose detection would confirm that gravity is quantum mechanical in the same way electromagnetism is quantum mechanical, and whose theoretical description requires a consistency that no one has yet achieved. It is simultaneously one of the most certain theoretical predictions in physics, and one of the most inaccessible objects in nature. It cannot be detected with any instrument we can build or conceive of building. It cannot be described by any consistent mathematical theory we currently possess. It lives at the intersection of our two greatest intellectual achievements and embodies their most fundamental incompatibility. The history of physics is a history of unifications. Newton unified terrestrial and celestial mechanics. Maxwell unified electricity and magnetism into electromagnetism. Einstein unified space and time into space-time. The electroweak unification of Glashow, Salam, and Weinberg brought electromagnetism and the weak force together into a single framework. The Standard Model unified that electroweak theory with quantum chromodynamics, describing the strong force. Each unification revealed that what had appeared to be separate phenomena were aspects of a single deeper structure. Each one changed how we understand the universe at a fundamental level. Each one was accompanied by specific testable predictions that were confirmed by experiment. The unification of quantum mechanics and general relativity, the construction of a consistent quantum theory of gravity, is the unification that has not yet happened. It is the step that remains. And the graviton is the particle that symbolizes that missing step. Not merely because it is undetected, but because the theory that would fully describe it does not yet exist. Because every mathematical approach to writing down that theory has either produced infinities or required unconfirmed structures like extra dimensions and supersymmetry, or produced a framework so mathematically intractable that extracting testable predictions has proven beyond our current capabilities, or raised questions so fundamental about the nature of space and time that answering them requires conceptual tools we have not yet invented. You have been held in your chair throughout this entire exploration by a force whose quantum description has defeated every attempt to write it down consistently. Every other force that acts on you has a confirmed quantum particle. Photons mediate the electromagnetic forces holding your atoms together. Gluons bind the quarks inside the nuclei of those atoms. W bosons enable the nuclear processes that ultimately power the sun whose light falls on you. And gravity, the force so familiar you feel it every moment of your existence, the force that holds the planets in their orbits and shape the large-scale structure of the entire observable universe, is described classically with extraordinary precision and quantumly not at all. The graviton may exist. On theoretical grounds, it almost certainly must. Its mass must be essentially zero. It must travel at the speed of light. Its spin must be 2. It must couple to everything in the universe with a strength so small it can never be directly observed. It must be the quantum of a field that is not merely a field in space-time, but is space-time itself, and a consistent mathematical theory describing its full quantum behavior, a theory that could stand alongside quantum electrodynamics and the Standard Model as a confirmed description of nature, does not yet exist. That is not a failure of ambition or attention. Some of the most gifted mathematical minds of the last 100 years have devoted their careers to this problem. It is a reflection of the genuine depth of the question. The graviton is not a missing piece waiting to be slotted into a completed puzzle. It is the piece whose shape reveals that the puzzle itself is more complex than we thought, that what we have built, magnificent as it is not yet finished, and that the next step requires understanding the universe at a level of depth we have not yet reached. The universe has given us 2 perfect descriptions of reality, and in the silence between them, where gravity and quantum mechanics should agree and do not, the graviton waits.